A MOSFET is another type of transistor. This is a metal oxide semiconductor field effect transistor. So it's a long name, but we shorten it to MOSFET. It's also made of N-type and P-type silicon, but with a slightly different structure. So this is the basic structure here. I have these two wells right here that I've drawn in green that are heavily doped N-type silicon. And then the rest of the bulk substrate is basically P-type silicon. And then here's where the name comes from. I have an oxide layer, and then what's typically now polysilicon, but in the old days was metal, so that would have been my metal layer here, so metal oxide semiconductor, hence the first part of the name. The second part of the name comes from when I apply a voltage on this metal, what we're going to call the gate right here. So this is going to be my gate. When I apply a voltage there, I can basically pull electrons into this region, creating a channel using the field effect. So this is my channel now, and that creates a conducting path between these two terminals right here. So that's the rest of the name, field effect transistor. So this particular one with these N+ wells right here is going to be an NMOS or N-channel MOSFET. And the same device with P+ wells right here that can create a channel with holes right here, and this is an N substrate. This is going to be called a PMOS or P-channel MOSFET. And the symbol that I'm going to use for these typically is going to look something like this. For the NMOS, I have my 3 terminals right here. For the PMOS, and I have my arrow pointing down here. The PMOS, it looks the same, I just have a slightly different direction for that arrow. And for the actual terminal names, I already gave you gate right up here, so this is also the gate on this side. And the gate is going to be this terminal going into this thing that looks like a capacitor here. And it looks like a capacitor for a reason, right? It's effectively a capacitor at the input. So this is going to be my gate for both the NMOS and the PMOS transistors. Then my source is going to be the side with the arrow right here in both. And so that could be either of these sides. It's a symmetric device right here. And then the drain is the other side. You will occasionally see these drawn slightly differently. And confusingly, the arrow is pointing in the different direction toward the gate here, and away from the gate in the PMOS version. So you'll see a lot of different schematics, but these are 2 of the most common ones, and I'm going to use the ones that I drew up on top here. But one of the reasons that I wanted to show you this is that one of the things you might see is that I've drawn these as a 3-terminal device, right? I've got my gate, I've got my drain, and my source, or GDS. But I do have, truly in here, I have a 4th terminal right here. If I look at this bit right here, this is the body terminal. This one is typically connected directly to the source, right? And so I typically just don't even think about this. But in certain transistor configurations, they will give you that 4th pin. But it's pretty rare. So most of the time you'll still just see the 3-terminal device with a gate, drain, and source. Okay, and key differences between the MOSFET and the BJT, beyond the kind of general physics of it and the different names for my terminals, in this case the MOSFET is voltage controlled with that gate voltage. Whatever voltage I apply to the gate is going to control my transistor behavior. Another key point is that when it's on, it looks a lot more like a small resistor than a fixed voltage drop like I had in my BJT. So effectively this turns into a small resistor that I'm going to call RDS, or the drain source resistance, than the fixed voltage drop that I get between the collector and the emitter in my BJT. There are a lot of reasons why you might choose one or the other in terms of BJT or MOSFET. MOSFETs are great because of this small resistor right here. I can effectively have a smaller voltage drop across the source and drain of a MOSFET than I could across a BJT, so I can have a more efficient switch. A BJT can switch a higher voltage typically because of this effectively reverse diode that I have here than a MOSFET can. There are MOSFETs that can switch pretty high voltages as well, but they're, once again, less common. MOSFETs typically cost a little bit more than a BJT, but a BJT needs that resistor at the base, and I don't need something similar for the gate of a MOSFET. So once again, pluses and minuses, it really depends on the application as to whether or not there's actually a better choice. Typically you go with what you're most comfortable with. We can also create a matrix for MOSFETs looking at how they turn on and off. So I'll look at both NMOS and PMOS and look at how I keep them off and how I turn them on. Similar to the VBE voltage that controlled the on-off behavior of a BJT, I'm going to have a gate source voltage that's going to define whether my MOSFET is on or off. So in this case, I have some VGS defined between the gate and the source. And in a PMOS transistor, I define that the other way. The source is going to have the higher voltage right here. But really, the key point is that that needs to be defined as less than some threshold voltage. And I'm going to define that as VTH. So VTH is going to be the threshold voltage. And this is going to be process dependent. Basically, the process that's used to manufacture the transistor will determine that threshold voltage. Both the kind of design and the process is going to determine a threshold voltage. So that's a value that you'd look up in a data sheet for a particular transistor. Right? But once I know that threshold voltage, I can see if my gate to source voltage drop is less than or greater than that. And if it's less than that threshold voltage, then I'm always going to be off. And when I'm off, my drain current that I'm defining between my drain and my source is going to be approximately 0. And that's going to be true for both the PMOS and the NMOS devices. So a typical threshold voltage that you might see in a MOSFET might be somewhere around 4.5 volts, but there are a lot of even smaller threshold voltages that are available now in different technologies. So you might get something even as low as a volt or so for certain transistors. When we're at the more interesting stage, when our gate source voltage is greater than that threshold voltage, then of course we're actually going to have a drain current that's going to be greater than 0. And I'm also going to have a very small RDS on. So you can find this in the datasheet, often defined as R drain source, this kind of equivalent resistance between the source and the drain. When it's in its on state, I'll have a small resistor there effectively. And the same thing for the PMOS transistor. So I have a small drain source resistance in the on state, and I'll therefore have a drain current that's much greater than 0. But similar to the BJT, I can use a voltage at my gate to switch a very large current, and then I could use that to drive a motor or a lamp or some other thing that requires high current like a speaker. I can also look at the on behavior for a MOSFET. Similar to a BJT, it's not completely straightforward. And in this case, I'm going to look at my drain current versus the drain source voltage. So that voltage drop across my two primary terminals there and the drain current going into that. And I can plot that for several different VGSs, several different effectively gate voltages that I might have on this. Right, so these are somewhat poorly drawn curves, but these are for increasing gate source voltage. I'm going to get more drain current through my transistor. And I once again have two different regions that I can look at here. And to really blow your mind and confuse you, this is opposite of what it was in the BJT case. So in this case, I can effectively change my drain source voltage and I get no change in drain current. So we call this the saturation region. So that saturation region for a MOSFET is occurring at high drain source voltage drop. And down in this region, because we effectively get a linear change between my drain source voltage and my drain current, this one we're going to call the linear region. So once again, it's effectively acting like there's a small resistance there. So if I want to use the MOSFET as a switch, then I'm typically going to once again want to operate in the region where I have a small voltage drop across my transistor so that I get as much voltage drop as possible across the device that I'm trying to switch. And so for a MOSFET, I'm going to want to operate in this linear region. Right? That's giving me the point where it's effectively operating like I have a very small resistor between my drain and my source. Let's look at this used in an actual example. So I'm going to use the same example that I did for the BJTs. In this case, I'm trying to drive a motor that has a resistance of approximately 100 ohms. I'm trying to drive that with my Arduino. And in this case, I have a transistor that is going to have a drain source resistance when it's on of approximately 100 milliohms. And I'm also going to assume the threshold voltage for this transistor is 4.5 volts. I should also mention that this particular topology, when I have this transistor at the bottom and connected to ground, is often called the common source topology because the source is connected to my common or ground. It's also called low side drive, so it's on the low side of this particular circuit. All right, but one of the things that I can see from this immediately is if my Vin is 0 volts from the Arduino, then my VGS is also going to be 0 volts, right? 0 volts and 0 volts. Then that means that my transistor is going to be in its off state, right? And so I have no drain current here and my motor's not going to turn. If I set my input voltage to 5 volts, then my VGS is going to be 5 volts. That is greater than 4.5 volts, which is my threshold voltage. So now my transistor is going to be on, which means that I have this drain source resistance also on. And so I can calculate the drain current that I get, and therefore the voltage drop I'd ultimately get across this resistor. So let's calculate the drain current first. So the drain current that I'm going to get here, right, that's this current right here, is going to be based on these two resistances and the motor voltage that I'm applying. So this is going to be my motor voltage divided by the total resistance, which is going to be my motor resistance plus that drain source resistance. And it's going to be pretty close to 100 milliamps. It's going to be actually about 99.9 milliamps. My VDS, of course, is just going to be that drain current times that RDS when it's on. So I could have also thought of this as a resistor divider. I am doing effectively the same thing here. Right, and this is going to give me approximately 10 millivolt drop across my transistor here. And if I compare that to the BJT that I was looking at earlier, remember I was getting a collector emitter voltage drop of about 200 millivolts, right? So I can have a much smaller voltage drop in a MOSFET, which is one reason that people sometimes choose a MOSFET to drive a motor. It's also pretty small, which is going to be putting me in that linear region, so my assumption that I get this drain source resistance and it acts as that nice resistor there is valid.